So now we're going to investigate how to actually derive vector equation of a plane. So for example, if you have a diagram as such and you are given a plane, so example, assume this is a plane, right? And you're given vector AB, you're given vector AC, AR, and R is basically any point on the plane, on this particular plane, right? So R is a point which is on this particular plane. So in this case, as you can see, R is over here. Assume it's any point on the plane, and AB and AC, AB, AC, and AR are coplanar. Coplanar simply means it's on the same plane, yeah. Okay. So in this case, based on this diagram, your AR, this vector AR, from the basic law of vector addition, it is AB add with AC. When you add AB and AC, the resultant will be AR. Okay. So in this case, we are assuming AB because we are not sure of the magnitude. So we assume it is constant T multiplied by vector AB and constant U multiplied by vector AC. So in this case, AR is TAB plus UAC. And next, we will use the basics like AR is R minus A and AB is B minus A respectively. AC will be C minus A. And when we substitute, we can actually reduce this equation to this form, bringing the A over. And if we further simplify it, we can actually interchange it to R equals to, we're expanding this and rearranging it. So we're going to collect the coefficients of related to vector A together and vector B and C respectively. So we rearrange this equation, expand it, and collect all the coefficients of A together and then B and C together, right? So we will reduce our vector equation of a plane and write it in such a form, right? So we will use this form to determine vector equation of a plane if we are given sufficient information. So in this case, this is a vector equation of a plane, right? It's specifically known as vector equation because it's written in the form of a vector. So provided point A is basically a common point between AB and AC, that's why it's point A. So point A has to be on the plane, and obviously B and C are vectors which are parallel to the plane. Okay, so now we will actually see how to determine a vector equation of a plane and how do we actually find the corresponding point given the values of T and U for a particular equation of a plane. Right. So for example, you are given point ABC. So point ABC, they are points. You have to convert them to vectors in order to find the vector equation of a plane. So you can simply assume vector OA. So vector OA is A minus O, and we labeled it as vector A here. So A minus O, you will get 1, 2, negative 1 respectively. And same goes with vector OB is B minus O and vector OC is C minus O respectively. Right. So after you convert the points to vectors, your next step here would be to actually use the general equation of vector equation, which is in this form, right? So now you have your A, which is this, and then you have your B, which is this, and you have your C here. So your next task would be just substitute accordingly into the formula. So that's what we did over here. 1 minus T minus U, right? It's first part of the formula, and then we substitute our A, which is 1, 2, 1, substitute B, and substitute C correspondingly. All right, you substitute accordingly, and then your next step would be expand it and simplify, right? So you expand it just like a normal addition of vectors, right? Expand, and it's as simple as 1 minus T minus U multiplied by 1. You will get this. Okay, and then negative 2 times t, you will actually get negative 2t, and 4 times u will be actually 4u. Right, and then you follow up to add up your y and your z respectively, and then reduce and simplify your added vectors in terms of u and t until the simplest form possible. So that will be your the equation of plane for part A. For part B, you're required to find the point on the plane which corresponds to the value of t and u given. So the t is 2 and the u is 3. So you can simply substitute t as 2 and u as 3 into your vector equation of a plane, right, which you obtain. And then once you substitute, you can actually get a point. So the required point is 4, 13, 4 respectively. It is just named R. You can name your point with any capital letter. Okay, now we have found the vector form of an equation of a plane. So now we are going to determine how to find the Cartesian equation of the plane, provided you are given the vector equation. So we are going to convert a vector equation of a plane, which is given in this form, right, um, to the Cartesian equation. So what is a Cartesian equation? Cartesian XYZ axis is a Cartesian axis, right? So you need to convert this into x, y, like say AB plus BY plus CZ equals to K. So we need to find a K in the end for a plane equation. So recap back, that particular K is a dot product of the normal to the plane, right? The normal vector to the plane and a point that lies on the plane. So we need to work out from this vector equation to determine the normal to the plane and also the point that lies on the plane. Only then we can actually come up with the Cartesian equation. So first step here, you need to actually expand this form of vector equation. So once you expand, um, you need to open up all the expand it into individual forms, and then collect the terms which are related to t and u in order to express it in component form. So once you expand it, as you can see, we have collected the vector which is related to I, j, and k individually, and then we have collected the terms that are related to t and terms which are related to u, and we have separated them. So recap back, R, okay, by definition, vector equation of a plane, R equals to the vector A. So the vector A here is represented by 2i plus j plus 3k, which is 2, 1, and 3, okay, written in component form. And then t is multiplied by coefficients of t, I, j, k respectively, is this part here, which is 1, 1, negative 1. Okay, and then followed up by u, which is multiplied by coefficients of I, j, k respectively for u as x, y, z. Right? So once you write it, express it in component form, and then you can proceed further. Okay, so based on this equation, if you compare it with the form which is given in the vector equation of a plane, r equals to a plus tb plus uc. So based on this, you can identify a point and you can identify the normal vector to the plane. So in this case, so the point here basically is 2, 1, 3. All right, the point is A, right? Okay, so the point A is 2, 1, 3. It's a point. Okay, and there are it involves two vectors which are 1, 1, negative 1 and 3, negative 3, negative 7. So it involves these are the two vectors which are lying on that particular plane. So we are very sure these two vectors lie on the plane, and point 2, 1, 3 actually is a point that lies on the plane. So moving on, we can find the vector which is normal to the plane by simply having a cross product of the two vectors. Right, so once you have a cross product of the two vectors, use the shortcut method that I've explained in my earlier slides to identify the normal vector in terms of ij and k. Right, so you've got -10, 4, and -6 respectively. So you're going to use point 213, which we identified just now, to determine the k. So the k is always a dot product, pay attention, of the normal vector, is obtained from here, and the point on the plane. Okay, so multiply both is a dot product, so the resultant should be a number. Okay, so we have got the number. So based on that, we can use the normal vector as the coefficient of x, y, and z. Right, so we can get -10x plus 4y minus 6z equals to the dot product, which is -34. So this will be the vector equation in the Cartesian form. Vector equation, sorry, it's a Cartesian equation of a plane, right? So, or you can simplify this by dividing everything into 2, and you can get this as your plane equation in the form of Cartesian equation.